Well, this is section 5.1. Chapter 5 is the last chapter we're doing in Calc 1, so we're beginning into the last chapter. And this is the section where we start doing things backwards, the thing that I've been warning you about all semester. Okay? All semester we've been taking derivatives up till now. Now we're going to begin taking antiderivatives. So in section 5.1, we're going to take a look at the idea of antiderivatives and the indefinite integration process. And so our objectives are to write general solutions for differential equations and use indefinite integration notation, to use basic rules for antiderivatives, and find some particular solutions. All right, so let's first start out. Beginning of a new chapter, 5.1, some definitions, some new terminology. Right? Antiderivatives. The problem that we have in this section, the thing that we're going to be requested to do, the challenge that we have to face is we are going to be looking to find a function. Now, this is one of the things about calculus that I don't like, but every calculus textbook I've ever seen does this. We are going to be using the capital letter F and the lowercase letter f in a definition about functions. So there's big F and there's little f. Okay? There's big F and there's little f. Okay, and our problem, the thing that we're going to do in Chapter 5 for the rest of the semester, the thing that we're going to do is we're going to be trying to find a function, big F, whose derivative is a known function, little f. So up till now, we've been handed a function and asked to find its derivative. Now, we're going to be handed the derivative and asked to go backwards and find out where this came from. Find that function f, big F, whose derivative is a function that is known, little f. And that's only if it exists, because there are some situations where you are going to have a function, little f, where there is no function to go backwards to. Now this, I don't think we ran into this at all when we took derivatives. I don't think we had a single situation where you were given a function and said, find the derivative, and you said, I can't. Right? We might have needed to find new rules or new approaches to find these things, like when we did implicit differentiation, or when we used implicit differentiation to find derivatives of inverse functions, things like that. But there was nothing we ran into where here's a function and you said, I can't find a derivative. Right? But that is possible when it comes to antiderivatives. It is possible that a function f will, I want the highlighter, that a function f will not exist, right? Or that a little f might not have an antiderivative. All right, so here's our definition. A function big F is called the antiderivative of little f on some interval. Now that can be a tiny interval or that can be the entire real numbers, just depends on the function, when the derivative of big F is equal to little f for all of the x's in that interval. Okay? Now I want to point out something here that I'm hoping you saw, but you may not have, and that's okay. The article that we use right there. We use the article an, antiderivative. Right? And in the English language, the article an in front of some noun means that this is one of potentially many. So a function little f could potentially have several antiderivatives. Okay? So please note that the function f that we're working with here is called an antiderivative and not the antiderivative, because someone else working on the same problem could find a different antiderivative. Just depends on the function. Now, for many functions, there's one obvious antiderivative, but there are some functions out there, some little f's out there, where depending on how you look at it and how you treat it, there are antiderivatives that exist that look nothing like each other. Okay? All right, so representation of antiderivatives. If big F is an antiderivative of little f on some interval, and then big G is also an antiderivative on that same interval, then f and g only differ by a constant. All right, let's take a second and see if we can figure this one out. We are going to be given a single little f. And two different people are going to find antiderivatives. One person's going to find big F, another person's going to find big G. They are both going to be antiderivatives because they're going to fit this definition. That is, G prime of X will be equal to little f, as well as F prime of X will be equal to little f. Both of those things will be true. And if both of those things are true, then this relationship must be true. That is, that G of X must be equal to F of X plus some constant value C. What do we mean by a constant value? Constant value C means something like a 3 or a 5 or a -2 or something like that, some numerical value. Because remember, right? Remember derivative rules. Right? If I were to differentiate this equation with respect to the variable x, the left-hand side would become G prime of X, the right-hand side would become F prime of X, and the derivative constant is always 0, and so we just wouldn't write it, and we would get the statement then that G prime is equal to F prime, or that little f of x is equal to little f of x. And where did I get that from? Well, that was the definition of the antiderivative. That if G, big G, was an antiderivative, it meant that G prime was the same thing as little f. So, f and g are two antiderivatives of a function f, little f. That means that f and g are the same function, just one of them has been, and I'm going to throw back to college algebra here, one of the functions has been vertically translated, a vertical translation, because adding a constant to a function is a vertical translation. Right? It moves the graph up or moves the graph down, but it won't change the shape of the graph. And if it doesn't change the shape of the graph, it doesn't change the slopes for the function. And if it doesn't change the slopes for the function, then it is the same function, essentially, just vertically translated, but the derivatives would be the same. All right, so we're getting the terminology down. Okay? An antiderivative is any function f of x such that f prime of x is equal to f of x. An antiderivative is any function big F such that big F prime is equal to little f. Okay? The general antiderivative. Right, now, depending on who wrote the textbook, is sometimes referred to as the most general antiderivative, or the general antiderivative is said to be f of x plus a constant such that f prime is equal to c. And adding this constant right there, adding that c right there, takes into account this problem that we have up here with where f and g could both be antiderivatives. Because if we just say, well, it's this function plus any constant you want, then, right, we take care of that vertical translation issue. Right? So here's the idea. Someone is going to hand you a little f function, and they're going to say, what is the general antiderivative? And so you are going to find a function f of x such that f prime is equal to your little f, and they're going to say plus c. Right? We'll worry about this one here in a moment, this general differential equation one. Right? All right, so let's take a look at the directions. The directions say to find the general antiderivative. So I know that no matter what, my final answer is going to have a plus c on the end, because that's the general antiderivative. Now the function part that goes in front of that is going to be the f of x that I need to have to make this thing work. So for example, in this first one, I need a function big F whose derivative is sine. So I'm going to dig into my knowledge here. I'm going to dig into what I know to be true. And I am going to find a function whose derivative is sine. All right, so let's see. I know the derivative of cosine is negative sine, So then the antiderivative of sine should be negative cosine. So then my function f, big F of x, is negative cosine plus c, because the derivative of negative cosine is sine. And the way that I check my work is I just make sure that this is true. That if I take the derivative of that, what I get back to my little f that was given to me. Okay. All right, how about this guy over here? F of x equals x squared. So I want something where the derivative is x squared. Let's see. I know the derivative rule for exponents. It says multiply in front by the exponent and then subtract 1 from the exponent. So if taking a derivative means subtract 1 from the exponent, then taking an antiderivative would mean to add 1 to the exponent. So I know I'm going to get an x cubed. And so I'm going to check and see if that's right. Is f of x equal x cubed plus c? If I take the derivative, big F prime, I'm going to get 3x squared. And what I really want is just x squared. So I've got this 3 there that shouldn't be there. So I'm going to fix that by putting in a 1/3. So that when I take the derivative, that 1/3 cancels out with that 3. And now I've found my general antiderivative. And I'm just going to keep doing this as I work through these. All right, g of x is equal to, whoa, g of x, does that matter? No, it just means I'll call the general antiderivative big G. Okay. Now, what function gives you 1 over x when you take its derivative? Well, that's natural log. So that means that the antiderivative of 1 over x is natural log x plus c. H of x, does that matter? Nope. Just means I'll call its antiderivative big H. And what function, when you take its derivative, gives you e to the x? My favorite, e to the x. Okay. So what I'm doing in this section is I am just taking everything that I've done so far, and I'm doing the inverse. I'm doing the opposite of taking a derivative. I'm taking an antiderivative. Okay. This next section is about finding general solutions to differential equations. That'll be in part 2 of this video.